Hello, and welcome back to the deep dive. Wow, it feels like ages since our last one, doesn't it?
It really does. Good to be back, though.
Absolutely. And trust me, this one is definitely worth the wait. So whether you're driving, maybe working, or just, soaking up some knowledge, we've put together a really comprehensive, in-depth look at large language models.
Yeah, this is designed specifically for you, the AI expert listening in.
Exactly. We're aiming for the ultimate all you ever need summary of LLM terminology, really digging deep into the concepts that actually matter to practitioners and researchers.
We've really sifted through, just a mountain of recent research, haven't we, to bring you this, well, compact but still incredibly thorough overview.
Yeah.
Our mission today really is to cut through all the noise, give you a systematic understanding of the fundamental stuff, sure, but also the advanced topics right at the frontier of LLM research.
And we're drawing insights from, a whole collection of really informative summaries and papers.
Extensive stuff.
Yeah. Okay, so let's unpack this a bit. Today, we're basically embarking on a journey through the, let's say, intricate world of LLMs. You'll gain a deeper understanding of, well, everything. From their core architectural components, the complex training paradigms.
Right, how they're actually built and trained.
To the advanced adaptation strategies, the cutting edge of augmented and multimodal systems, and, of course, the crucial challenges facing the field. This isn't just a surface-level scan. We're diving deep into the why and the how of these powerful models.
Absolutely, getting into the nuts and bolts.
So here's a quick glimpse of what we'll be covering. First, the foundational pillars of LLMs.
The basics, but crucial.
Then, architectural innovations and training deep dives. That's where it gets really technical.
Yeah, the fun stuff.
Third, adapting and optimizing LLMs, making them work in the real world.
Efficiency and specialization.
Fourth, expanding horizons. Augmented, agentic, and multimodal LLMs, moving beyond just text.
Interaction, perception.
And finally, navigating the LLM landscape. Applications and challenges, where are they used, and what are the big roadblocks?
A big picture.
Okay, so grab your favorite beverage, get comfortable, and let's get started on this deep dive.
Let's do it.
All right, so to truly understand LLMs, we really need to go beyond the surface, don't we? They're not just scaled-up versions of older language models. They represent a fundamental shift in how we approach AI.
That's a key point. It's a paradigm shift, really.
And what's truly fascinating, I think, is how concepts like the distributional hypothesis, which, has been around since the 1950s.
Telegaris, yeah.
How that actually laid the groundwork for their very essence. It's amazing how these old ideas find new life.
Absolutely. At their core, large language models are, well, sophisticated neural networks.
Yeah.
They're trained on incredibly vast textual corpora.
Just massive data sets.
Massive. And what really sets them apart from traditional language models is their incredible adaptability across a broad spectrum of linguistic applications. This versatility, for you, the expert, is really enabled by two core characteristics.
Okay, what are those?
First, the revolutionary transformer architectures. We'll definitely get into that.
Yeah.
And second, the power of self-supervised training on these enormous data sets, often hundreds of billions of words.
Wow.
And that allows them to internalize just substantial statistical knowledge about language patterns. They learn the structure implicitly.
Okay, so drilling down into that, the first pillar is understanding how they grasp meaning. Let's talk about meaning and representation beyond the surface. The cornerstone of this seems to be the distributional hypothesis.
Precisely. The distributional hypothesis, first articulated by Zelikaris back in 1954, posits that, and I'm quoting here, words that occur in the same context tend to have similar meanings.
Right. Words are known by the company they keep.
Exactly. And this isn't just some linguistic observation. It's really the bedrock for how we computationally model meaning in LLMs today.
It's so foundational. And computationally, this translates to what words with similar distributional properties have similar meanings.
Correct. So if
Yeah.
you're thinking about how this is operationalized, it's about looking at sets of co-occurring words within a corpus.
Okay.
This could be within a fixed window of, say, AND tokens around a target word, or even through more complex syntactic dependency relations.
Right. And what's striking is the strong interpretation of this hypothesis, right? Which suggests that humans themselves might derive word meaning from these very distributional patterns.
That's the idea. It really grounds the artificial intelligence approach in a potentially profound cognitive principle. Whether it fully explained human meaning is debated, of course, but it's powerful for computation.
Indeed, and its relevance is huge. It provides the fundamental theoretical basis for representing meaning geometrically in vector spaces, which is absolutely central to how large language models function.
Couldn't agree more. Without this hypothesis, the whole concept of semantic similarity in computational models would be fundamentally different, maybe impossible in its current form. It allows us to move from abstract words to quantifiable relationships in space.
Which brings us directly to embeddings, mapping meaning to space. So when we talk about an embedding, what are we really talking about? It's a representation of units, words, sentences, texts,
Right? Any unit of language.
as real valued vectors in a high-dimensional vector space. So think of it literally as a point in this vast semantic space.
Yeah, a point where proximity implies similarity. It's like creating a semantic map where related ideas cluster together.
And the primary purpose of these embeddings is, like you said, to calculate that distributional similarity.
Exactly, and what's particularly powerful is that these embeddings can be pre-trained on massive corpora using unsupervised large language models.
Right, the self-supervised part.
Right. This process allows them to learn generic representations that are highly versatile and shareable across a multitude of tasks. It gives them a foundational layer of understanding without needing explicit labels for everything.
And this is where we get to the sort of magic of word embeddings, which really cemented that link between vector space operations and the semantic or syntactic properties of words. Models like Word2Vec.
Mikolov and colleagues, yeah, 2013, that was huge.
That's where that famous analogy comes from, right? The king, man plus woman, queen thing.
That's the one. It's such a vivid demonstration of how these models can learn and represent these latent semantic relations, even without being explicitly trained on, monarchy or gender relationships. It's a remarkable emergent property.
Absolutely. And building on that, sentence embeddings are numeric representations of entire sentences as vectors, crucially contextualized embeddings like we see in models such as BERT.
Right, BERT was key for context. Exactly. They combine these static word embeddings to convey context-dependent meaning for each token within a sentence. So the same word bank, for instance, used in different contexts.
Riverbank versus financial bank.
Precisely. You will have a subtly different numerical representation, capturing the nuance of language that traditional static word embeddings often missed.
Now, none of this geometry works without the underlying mathematical foundations of vector spaces. So in these models, units, words, documents are represented as vectors in an n-dimensional space, applying linear algebra to language.
Right. And when you have a collection of M units, this naturally yields an MXN matrix. For traditional bag-of-words models, corpora are typically represented as document term matrices, simple counts.
Yeah.
But for word vectors, it's an MXN matrix where each word itself is an n-dimensional vector, a distinct point in this semantic landscape.
And the true computability, the real power here, comes from how easily we can calculate similarity, right? Things like word meaning or even stylistic similarity between documents.
Quantifiable.
Can be quantified using classic geometric distance measures. We're talking Manhattan distance, Euclidean distance, or the very common cosine distance.
Cosine similarity is everywhere in this field.
Yeah.
It measures the angle between vectors, ignoring magnitude.
It's truly incredible how these simple geometric operations in this abstract high-dimensional space can yield such profound insights into the very fabric of language.
Really is. It connects math and meaning in a very direct way.
Okay, so moving on from foundations, here's where it gets really interesting for our expert audience, I think. The secret sauce behind LLM's immense power largely lies in their architecture and how they're trained. We're not just talking about scaling up, we're talking about fundamental changes in how these models process information and learn.
Precisely. The transformer architectures were definitely the cornerstone, but the advancements extend far beyond just that initial paper. The sheer scale we're dealing with now necessitates sophisticated distributed training methods and really meticulous data preprocessing.
Can't just throw garbage in.
Absolutely not. Garbage in, garbage out, magnified. And this is coupled with constantly evolving training objectives. It's a complex dance between raw power and refined technique.
Okay, so let's dive into architectural innovations and training deep dives. The original paper, Attention is All You Need, that really defined a new era, didn't it?
It truly did. A landmark paper. This architecture has become the gold standard, not just for NLP, but also for image processing, multimodal models. It's everywhere.
And its core design involves an encoder and a decoder, each made up of these repeated blocks.
Right. And the main mechanism, the revolutionary part, is multi-head self-attention. This meticulously checks connections between every input element, weighting those that are important for the task at hand.
And the multi-head part.
That signifies that this process happens in parallel. It allows the model to highlight different task-relevant aspects simultaneously, maybe focusing on semantic relationships in one head, syntactic in another.
Got it. So it looks at the input from multiple angles at once.
Exactly. And unlike earlier sequential architectures like RNNs, transformers process data in parallel, which is enabled by these positional codings we'll talk about.
But the original limitation was that quadratic complexity, right? The ON2 thing.
Yes, the complexity of self-attention. Since each input element connects to every other, the computation grows quadratically with sequence length, which limited the practical input size significantly in the early days.
That complexity became a major bottleneck. So let's explore the architectural nuances in LLMs now, specifically this ongoing evolution or maybe tension between encoder-decoder versus decoder-only designs.
Right. Traditionally, the roles were clear. Encoder-only models, like BERT, were great for natural language, understanding tasks, classification, entity recognition, that sort of thing. Decoder-only models were typically used for natural language generation, like text completion. And encoder-decoder models were the go-to for sequence-to-sequence tasks, like machine translation.
But the LLM trend seems to favor decoder only.
It's striking, yeah. Many prominent models, GPT-3, Palm, Llama, Bloom, are decoder-only architectures. And despite that focus, they've demonstrated significant gains in both NLU and NLG tasks, really blurring those traditional lines.
But it's not totally settled, you said.
No,
Yeah.
definitely not. Counter trends exist. Models like T5 and UL2 have shown that encoder-decoder models can actually outperform decoder-only variants in some setups. Though, admittedly, increasing the size of decoder-only models can often close that performance gap.
So the future might be more flexible, maybe dynamic configurations?
That's what it looks like. Future LLMs could heavily leverage encoder-decoder architectures, perhaps with these clever mode-switching tokens, like we see in UL2, Alexa TM, and Code D5++.
What do those do?
They essentially tell the model which mode to operate in NLU mode, NLG mode, etc. This enables task-specific behavior within a single architecture and facilitates multi-objective training. It's about building a real multi-tool for language processing.
Very interesting. And another crucial nuance is positional encoding strategies. You mentioned these are essential because the attention modules themselves don't inherently understand word order.
Exactly. Without positional encodings, a transformer would see the input sentence as just a bag of words, losing all sequence information.
Yeah.
They're absolutely vital.
Right. And we've seen several variants here. Absolute positions, relative positions, even learned positional encodings. What are the common approaches in modern LLMs?
Well, two popular ones stand out. First, there's alibi, which stands for attention with linear biases.
Okay.
It subtracts a scalar bias that increases with the distance between tokens. This effectively makes the model pay more attention to recent tokens. A really neat side effect is that alibi enables zero-shot length extrapolation.
Meaning it can handle longer sequences than it saw in training.
Exactly, without specific fine-tuning for longer context. That's a big advantage. Then there's ROPE, or rotary positional embedding.
Rope.
This one rotates the query and key representations based on their absolute position, but it cleverly creates a relative encoding that decays with distance. You see ROPE used in lots of big models: GPT, NeoX20B, Palm, Cogen, Llama.
But you mentioned conflicting findings. There's no clear winner.
That's right. For example, the Bloom model found alibi to be superior for their setup, while the GLM-130B team identified ROPE as performing better. It really highlights the ongoing research and the lack of a universal consensus. The best strategy might depend on the specific architecture data scale. It's a reminder that this field is still very much in active development, constantly iterating on these fundamental building blocks.
Absolutely. Okay, digging deeper into how these models really work, we have to talk about attention optimizations. Beyond the standard self-attention, query, key value from the same block, and cross-attention used in encoder-decoders.
Where queries come from one part, keys values from another.
Right. There's been significant innovation aimed at improving efficiency, especially dealing with that quadratic complexity at scale.
Indeed. That ON2 complexity for large sequences quickly becomes computationally infeasible. So we've seen clever tricks emerge. Sparse attention was an early approach used in GPT-3, iteratively calculating attention in sliding windows to approximate full attention.
Making it less computationally heavy.
Right. More recently, techniques like flash attention have been game-changing. It minimizes the bottlenecks caused by GPU memory access by tiling the input for faster computation. That's used in StarCoder and many others now.
And for inference, you mentioned multi-query attention, MQA.
MQA is huge for deployment. It shares the key and value attention heads across multiple query heads, drastically reducing memory usage and speeding up the auto-regressive decoding process. And crucially, it does this with minimal performance degradation. You see it in PAL-M, LLM 2.
That sounds a significant win for practical use.
It is. And there's even multi-head latent attention, MLA, used in DeepSeek V2, which compresses the key value, KV cache that's the memory needed, during generation into a latent vector, further reducing inference costs and achieving faster throughput. Efficiency is just a constant driving force here.
Makes sense. Shifting gears slightly, another critical component, normalization layers. Layer normalization was in the original transformer, right? For faster convergence.
That's right, a crucial component for stabilizing training. But within modern LLMs, we frequently see variations. Pre-layer normalization, pre-norm, is very common.
Normalization before the attention block.
Exactly. Applied before multi-head attention and the feed-forward network. This has been shown to provide significant training stability, and you'll find it in models like GPT-3 and Llama.
Are there alternatives?
Yes. There's deep norm, which is actually a variant of post-norm, applying normalization after the residual connection. It was designed to address the issue of potentially larger gradients that can sometimes arise with pre-norm, especially in very deep models. GLM 130B used deep norm, reporting better fine-tuned performance.
Interesting trade-offs.
And some models, like Bloom and Alexitium, even use an additional normalization layer right after the embedding layer, just for extra stability, particularly at the start of the network.
This brings us to a really significant architectural shift. Mixture of experts. Mo, you said this isn't just about making models bigger, but changing the economics of scale.
Absolutely. The concept is quite ingenious. Instead of having one single massive feed-forward network in each transformer block, you have a variant with multiple parallel independent experts.
And these experts are essentially separate feed-forward layers.
Exactly. And there's a router network, usually a small gating network, that learns to direct each input token to only one or a few specific experts.
Yeah, so not every token goes through every expert. That's the efficiency gain.
Precisely. It's a sparse architecture. Only a few experts are activated per token during inference. This allows a dramatic increase in the total number of parameters in the model without a proportional increase in the computational cost for processing each token.
So you get the benefit of more parameters, potentially more knowledge, without the full computational hit.
That's the idea. Imagine building a model like GLAM, which had 1.2 trillion parameters, 7 times larger than GPT-3 at the time, but reportedly using only about a third of GPT-3's training energy. That's the kind of game-changing efficiency MOE unlocks. It allows for truly massive scale without the proportional carbon footprint or inference cost.
That's astounding. Are there other benefits?
Yes, several. MOE models often achieve comparable performance to dense models of similar computational cost, not just parameter count. They can be more efficient for fine-tuning, as you might only need to tune specific experts or the routers. Some research suggests they're less prone to catastrophic forgetting.
Forgetting old knowledge when learning new things.
Right. Which makes them potentially well-suited for continual learning scenarios. Plus, they can even allow for extracting domain-specific submodels, as Pangor demonstrated. You could potentially pull out the medical experts or the coding experts.
Fascinating. And we're seeing this used in many recent models.
Oh, yes. CPM2, DLAM, Pangoi were earlier examples. More recently, Mixtral 8x22b, Grok, models from the Gemini family, Snowflake Arctic, DeepSeek V2. It's clearly a major trend shaping the future of large models. It's a clever way to scale capacity more efficiently.
Okay, now let's turn our attention to the training pipeline. From raw data to robust models, this is where the real alchemy happens, transforming raw information into these highly capable models. And it all starts with data preprocessing, the foundation of quality.
Indeed. You can't build a skyscraper on shaky ground. Quality filtering is absolutely essential for achieving good results. If you train on low-quality data, you get a low-quality model.
Makes sense. How is it done?
Approaches typically fall into two main camps. There's classifier-based filtering, where you actually train another model on known high-quality data, like Wikipedia or curated books, to predict the quality of new text passages.
Using AI to clean data for AI?
Pretty much. Or there are heuristics-based methods, which employ rules based on things like language identification, text length, symbol-to-word ratios, keyword filtering, statistical metrics, trying to weed out noise and boilerplate content.
And then there's data deduplication. Why is that so critical?
It's critical for a couple of reasons. Firstly, duplicated data can actually skew the training process and prevent the model from learning optimally. Secondly, and perhaps more concerningly, excessive duplication increases the risk of the model simply memorizing chunks of the training data.
Which leads to privacy issues and poor generalization.
Exactly. So performing deduplication at various levels, sentence level, document level, or even across entire data sets, is a crucial pre-processing step to ensure the uniqueness and value of the training data. It's about making every piece of data count toward learning, not just memorization.
And what about privacy reduction, especially with web data?
That's a huge concern. Many large models are trained on vast scrapes of the web. To mitigate privacy risks, many LLM training pipelines employ heuristics-based methods to filter out personally identifiable information, things like names, addresses, phone numbers, email addresses, trying to prevent the model from learning and potentially reproducing private details later on. It's an ongoing challenge.
Okay, so once the data is cleaned and prepared, we get to pre-training objectives, what LLMs learn. This defines the actual task the model is trying to solve during that massive initial training phase.
Right. The most common objective is full language modeling, also known simply as autoregressive modeling or next token prediction.
Predicting the next word.
Essentially, yes. The objective is to predict the next token in a sequence given all the preceding tokens. This forces the model to learn the probabilistic structure of language, grammar, facts about the world, all implicitly, just by trying to predict what comes next.
Then there's prefix language modeling. How is that different?
It's a non-causal objective, often used in decoder setups like T5. Here, a prefix of the input is randomly chosen, maybe the first half of a sentence, and the model's loss is calculated only on predicting the remaining target tokens, the suffix. It focuses the model on sequence completion, given a specific starting context.
Got it. And of course, mask language modeling, MLM, famous from BERT.
Right. In MLM, you randomly mask out some percentage of the input tokens, or sometimes entire spans of tokens. And the model's job is to predict those masked tokens based on both the context before and after the mask.
Bidirectional context.
Exactly. This forces the model to learn a deeper bidirectional understanding of the language. T5, for instance, effectively masks entire spans of text, making the model infer missing chunks of information, which is a powerful objective called span corruption.
And some models combine these, like unified language modeling.
Yes. Models like T5 and especially UL2 pioneered this idea. They train the model on a mixture of objectives causal, next token, non-causal prefix, and masked language modeling, often using special tokens to signal which objective is being used for a given example.
So the model learns to handle different types of language tasks during pre-training.
That's the goal, to make the pre-trained model more versatile and better prepared for various downstream applications. In UL2's case, the mask LM variant used is often unidirectional, either left-right or right-to-left masking, which is a subtle but important distinction affecting how context is processed during that specific objective.
Understanding the relationship between resources and performance seems absolutely key at this scale. That's where LLM scaling laws come in, right? Defining the compute optimal balance.
Exactly. This field studies the optimal combination of model parameters, size, dataset size, and the amount of computational resources, like GPU hours or FLOPs, needed to predict how performance will improve as you scale up.
And there's a predictable relationship.
Generally, yes. It's been shown that the model's loss, how poorly it performs, tends to decrease according to a power law relationship as you increase model size, dataset size, or the compute budget. Essentially, bigger inputs often lead to predictably better performance, but the gains diminish eventually. It's not always intuitive how to best allocate resources.
I remember early studies suggested just making the model bigger was the main thing.
Yes, early work like Kaplan et al. In 2020 suggested that for a given compute budget, investing more in larger models was more important than investing in more data. They argued for highly compute-intensive large models trained for fewer steps.
But that changed with Chinchilla.
Right. The Chinchilla paper from DeepMind, Hoffman et al., 2022, presented a revised perspective. Their analysis suggested that for compute-optimal training, model size and the number of training tokens should actually be scaled roughly equally.
So more data became just as important as more parameters.
Exactly. They famously demonstrated that their 70 billion parameter chinchilla model, trained on 4 times more data than typical for its size at the time, could outperform the much larger 280 billion parameter Gopher model, despite using the same compute budget for training. That really shifted the focus from just bigger is always better to smarter scaling is better. It highlighted the importance of data quantity and quality alongside model size.
And the research keeps refining these laws.
Absolutely. More recent studies, like those from the DeepSeek team, have delved into various FLOP's budgets to determine the optimal balance of hyperparameters like batch size, learning rate, alongside model size and data scaling. Their findings suggest things like batch size should generally increase with compute, while the optimal learning rate tends to decrease. It's a highly empirical field, constantly refining our understanding of efficiency and optimal resource allocation for these massive training runs.
And to actually do these massive training runs, you need distributed training. This is really the scale enabler, isn't it?
Completely. You simply cannot train these models on a single machine, or even a few machines. You need sophisticated ways to distribute the work across potentially thousands of GPUs.
What are the main approaches? I know data parallelism is a common one.
That's fundamental. Data parallelism involves replicating the entire model across multiple devices, like GPUs. Then you divide each batch of training data among these devices. Each device computes the gradients for its portion of the data, and then the gradients are averaged and the model weights are synchronized across all devices.
Like having many workers doing the same job on different data pieces.
Precisely. But when the model itself becomes too large to fit on a single GPU, you need model parallelism. One type is tensor parallelism.
Also called horizontal or intra-layer model parallelism.
Right. This shards the computation of individual tensors like the large weight matrices in attention or feed-forward layers across different devices within the same model layer. They compute parts of the matrix multiplication in parallel.
Okay, and complementing that is pipeline parallelism, vertical parallelism.
Yes. Pipeline parallelism shards the model layers themselves across different devices. So device 1 might handle layers 1.8, device 2 handles layers 9.16, and so on. Activations are passed from one device to the next, forming a pipeline. This helps utilize devices when layers have dependencies.
Like a bucket brigade passing work down the line.
Good analogy. And when you combine tensor parallelism within layers and pipeline parallelism across layers, you get what's broadly termed model parallelism. This allows for efficient distribution of truly enormous models across a computing cluster.
Taking it even further, there's 3D parallelism.
Right. 3D parallelism combines data parallelism, tensor parallelism, and pipeline parallelism all together. This is the most commonly utilized training parallelism strategy in many leading LLMs. GLM 130B, Palm, OPT, Bloons, MTNLG all use variations of this to maximize resource utilization and train efficiently at scale.
Wow. Are there even more dimensions?
You could say so. We also have optimizer parallelism, often implemented using techniques like the Zero Redundancy Optimizer, or ZERO, developed by Microsoft.
ZERO, okay. What does that do?
ZERO cleverly partitions the optimizer state, which can be very large, especially with optimizers like Atom, the gradients, and even the model parameters themselves across the data parallel devices. This significantly reduces the memory footprint on each GPU, allowing you to fit larger models or use larger batch sizes. Bloom, for instance, relied heavily on ZERO.
So it's about memory efficiency as much as compute.
Exactly. And for the absolute cutting edge, some models like Pangua and Pangua have pushed this even further, talking about 5D parallelism. This essentially adds optimizer parallelism like ZERO and techniques like rematerialization or gradient checkpointing recomputing activations instead of storing them on top of the 3D parallelism. It's like a master chess player optimizing every single resource on the board.
Incredible complexity. Beyond just parallelism, specific training strategies and stabilization techniques are crucial for robust LLM development. Mixed precision training is common, right?
Yes, very common and very important for efficiency. This typically involves performing the forward and backward passes using lower precision floating point formats like FP16, 16-bit floating point, or BF16, BrainFloat 16.
Lower precision means less memory, faster computation.
Exactly. But you usually keep the optimizer states and a master copy of the model weights in the standard FP32, 32-bit precision, for stability during the weight updates. This significantly reduces memory usage and improves training throughput.
Is there a preference between FP16 and BF16?
BF16 generally offers better training stability compared to FP16 because it has a wider dynamic range, making it less prone to overflow or underflow issues with gradients. However, its adoption was initially limited by hardware support. You primarily needed NVIDIA A100 GPUs or newer or Google TPUs. FE16 is more widely supported but requires careful loss scaling to maintain stability. It's a balancing act between speed, memory precision, and hardware availability.
A persistent issue at this scale seems to be training instability, often showing up as sudden loss spikes.
Oh yes, that's a notorious problem, especially when training very large models for long durations. The loss might be decreasing nicely, then suddenly shoot up unpredictably. This often happens even with techniques like gradient clipping.
How do people deal with that? Just restart.
Sometimes restarting from an earlier checkpoint is necessary. But for more immediate recovery, common strategies include skipping the problematic batch of data entirely, or reshuffling upcoming batches to try and break out of the unstable state. Paul Am and Glam reported using these kinds of tricks.
Any other stabilization techniques?
GLM 130B found success by applying an embedding layer gradient shrink. Basically, they reduced the gradient specifically for the embedding layer because its gradient norm was often significantly larger than other layers, contributing to instability. And a general suggestion floating around for training larger models, 100B parameters, is to actually avoid using biases in the dense linear layers and the normalization layers, as this seems to improve stability.
Interesting. The initial setup is also vital, making weight initialization crucial for convergence and stability.
Absolutely. How you set the initial weights can make or break a training run. GPT-NeoX, for example, used a specific scaling factor when initializing the weights of their feed-forward layers to prevent activations from growing exponentially as they pass through deeper layers. Other layers use a very small initialization variance.
So small, careful initialization is key.
Generally, yes. The MTNLG team also validated that higher variance in weight initialization could lead to unstable training, reinforcing the need for careful, often small, initialization schemes. Galactica even suggested using longer learning rate warm-up periods specifically to help stabilize training when using standard random initialization.
Hugely important. It's generally recommended to use relatively low peak learning rate values for LLMs, typically in the range of, say, 1E4 down to maybe 8E4, combined with a warm-up phase, gradually increasing the rate, and then a decay schedule, gradually decreasing it, often a cosine or linear decay.
Does this need lots of tuning for each model size? It can. However, models like MTNLG and GPT-NeoX showed an interesting trick. They could often interpolate the optimal learning rate schedule based on the model size, drawing from patterns observed in previously trained models like the GPT-3 series. This can potentially save a lot of time and compute on hyperparameter tuning.
Clever. Lastly, what about mode switching? You mentioned this earlier. Adding special tokens during training.
Right. This involves adding task-related tokens at the beginning of the text sequence during the pre-training or fine-tuning stage. These tokens might signal whether the expected output is for a natural language understanding task, like classification, or a natural language generation task, like summarization.
And this helps downstream performance.
It's been shown to significantly improve performance on specific downstream tasks, as evidenced by models like UL2, UPaulM, and Alexa-TM. It's a way to explicitly give the model context about the type of task it's supposed to be performing, almost like a secret code telling it how to behave for that specific input.
Okay, so we've covered how LLMs are built and initially trained the architecture, the data, the complex training process. But their true utility often comes from how they're then adapted and made more efficient for specific tasks, right?
Exactly. While pre-trained LLMs possess remarkable generalization capabilities just from that initial phase, their core next token prediction objective doesn't inherently make them good at, say, following user instructions precisely, or avoiding problematic outputs.
They're not naturally conversational or aligned.
Precisely. This makes the adaptation phase absolutely critical. And for practitioners listening, understanding these techniques, fine-tuning, alignment prompting, is paramount for effectively utilizing these models and also controlling costs. It's about shaping that raw predictive power into precise, useful, and safe tools.
Let's break down the LLM adaptation stages. From pre-training to prompting, we've just discussed pre-training, that's self-supervised phase. The real customization often begins with fine-tuning, shaking behavior for specific tasks.
Right. And the most basic form of this is standard transfer learning. Even though pre-trained models are powerful, you can almost always improve their performance on a specific downstream task by further fine-tuning them on data relevant to that task.
Like taking a generalist doctor and training them to be a heart surgeon.
Good analogy. Models like T5 and MT5 are prime examples, showing how fine-tuning enhances performance significantly on benchmarks like GLUE or Super GLUE.
Okay, but then we get into more sophisticated fine-tuning, like instruction tuning. This seems really important for making models usable.
It's hugely important. Its purpose is basically to teach the model how to follow instructions and respond effectively to user queries in a natural language format.
How does that work?
The process involves fine-tuning the pre-trained model on datasets specifically formatted as instructions. Typically, this looks like an instruction, right? They summarize this text, maybe some input, the text itself, and then the desired output, the summary. You often use multitask datasets covering a wide range of instructions.
And the benefits are significant.
Very significant. Instruction tuning markedly improves the model's zero-shot generalization capabilities. Its ability to follow instructions it hasn't explicitly seen before. It boosts performance on many downstream tasks and even enhances cross-task generalization. And the compute cost for this stage is often remarkably small.
Like how small?
For instance, the Flan-Paul-M model reported that instruction tuning their massive 540 billion parameter model required only about 0.2% of the compute used for the initial pre-training. That's an incredible return on investment in terms of capability gain versus cost.
Wow. How are these instruction datasets created? Is it all manual?
Well, many early influential datasets were manually created. T2K Instruct focused on converting existing NLP datasets into various prompt formats. Later efforts like OPT-IML and the Flying collections curated much larger sets of tasks with more diverse prompting styles, including incorporating chain-of-thought examples.
But now AI is generating them too.
Exactly. That's a fascinating development. LLM-generated instruction datasets. The self-instruct papers show that you could prompt a powerful LLM like GPT-3 to generate new instruction tuning examples, and models trained on this synthetic data could actually outperform models trained only on human-created datasets.
AI teaching AI to follow instructions better.
Precisely. This method was used by popular models like Alpaca and Vicuna using outputs from GPT models. Evil Instruct took it further, prompting LLMs to iteratively rewrite instructions to make them more complex, leading to capable models like WizardLM and WizardCoder. It's a powerful way to scale up instruction data creation.
This seems to lead directly into the crucial topic of alignment tuning, ensuring helpfulness, honesty, harmlessness, HHH. Because even instruction-tuned models aren't perfect, right?
Far from it. The fundamental problem is that pre-trained LLMs, even after instruction tuning, are still prone to generating problematic outputs, things that are false, hallucinations, biased, toxic, or just unhelpful. They reflect the unfiltered nature of their training data.
So alignment is about making them behave better, according to human values.
That's the goal. Aligning these models with human preferences and values, specifically aiming for the HH criteria, helpful, honest, and harmless, and avoiding those unexpected, undesirable responses.
And the main technique for this has been RLHF, reinforcement learning with human feedback.
RLHF has been the prominent approach, famously used by OpenAI for InstructGPT and ChatGPT, and by Meta for Llama 2 Chat. It's typically a three-step process.
Okay, what are the steps?
First, you start with supervised fine-tuning, SFT, on a dataset of high-quality demonstrations, basically, examples of how you want the model to respond. Second, you train a separate reward model, RM. Humans rank different outputs generated by the SFT model for the same prompt, based on criteria like helpfulness, honesty, harmlessness. The RM learns to predict these human preference scores.
So the reward model learns what humans prefer.
Exactly. And third, you use reinforcement learning, RL, often an algorithm like proximal policy optimization, PPO, to further fine-tune the SFT model. The RM provides the reward signal during this RL phase, essentially guiding the LLM towards generating outputs that the RM predicts humans would prefer. Llama 2 Chat added refinements like dividing rewards for helpfulness and safety and using rejection sampling to improve diversity.
It sounds quite complex, involving multiple models and human labelers.
It is complex and data-intensive. That's why there's a lot of research into alternatives. One avenue is alignment with supported evidence. Here, the focus is specifically on reducing hallucination by training reward models to prefer responses that are grounded in and ideally cite external evidence, like web search results.
Building in a truth checker via the reward.
Sort of, yeah. Projects like GopherSite, WebGPT, and Sparrow explored this. Sparrow even used separate rewards for preference, how good the answer is, and rule following, is it citing properly, is it safe?
Are there ways to skip the complex RL part?
Yes, that's a very active area. Direct alignment with SFT, aiming to bypass the PPO step of RLHF. Techniques like DPO, direct preference optimization, REFT, reward ranked fine-tuning, PRO, preference ranking optimization, and RRHF, reward-ranked human feedback, work by directly training the LLM on pairs of preferred and dispreferred responses using clever loss functions, essentially baking the preference learning directly into a supervised fine-tuning process.
Simpler pipelines.
Potentially much simpler. And CoH, chain of hindsight, takes an interesting linguistic approach, using natural language feedback about why a response was good or bad instead of just numeric reward scores.
What about using AI for the feedback itself? Alignment with synthetic feedback.
Right. Given the cost and time involved in human feedback, researchers are exploring semi-automated processes. Constitutional AI, developed by Anthropic, replaces the human feedback loop in RLHF with feedback generated by another AI based on a predefined constitution or set of principles. They call it RLAF, RL from AI feedback.
So the AI judges itself based on rules.
In a way, yes. Alpaca Farm explored similar ideas, designing prompts to make LLMs generate feedback that mimics human preferences, even injecting noise to simulate human variability and mistakes. Self-align is another approach in this vein.
Can you achieve alignment just through prompting without training?
To some extent, yes.
Yeah.
Aligning with prompts involves carefully crafting the prompt to steer the LLM towards desirable responses. For example, self-correction prompting might first ask the LLM to identify potential safety issues with the query before generating the actual answer, significantly reducing harmful outputs. Concatenating instructions and chain-of-thought reasoning can also guide the model towards safer responses.
But even with all this alignment, models aren't perfectly safe, right? People try to break them.
Absolutely. This leads to the practice of red teaming, jailbreaking, and adversarial attacks. This involves actively probing LLMs, trying to find inputs, adversarial prompts or jailbreaks, that elicit harmful behaviors like generating misinformation, revealing private data, or bypassing safety filters.
Like security penetration testing, but for AI behavior.
Exactly. The data sets collected from these successful attacks are then invaluable for further safety fine-tuning, teaching the model to be robust against those specific kinds of exploits. What's even more meta is that powerful LLMs themselves can be used to automatically generate prompts to red team other LLMs, creating a continuous arms race for robustness.
Okay, let's shift from training and tuning to actually using these models. Prompting utilization. Guiding LLMs without extensive training. At its core, prompting is just how we talk to these models, right?
It's the interface, yeah. It's the method we use to query trained LLMs to generate the responses we want.
In the simplest form is zero-shot prompting.
Yes. This leverages the remarkable inherent zero-shot learning capabilities of large, pre-trained models. You simply give the model a task description or a question without providing any examples in the prompt, and it can often perform the task surprisingly well.
Like asking it to translate a sentence without ever showing it translation examples.
Exactly. It's truly remarkable how well sufficiently large models generalize to tasks they weren't explicitly fine-tuned for, just based on their vast pre-training.
Building on that, we have in-context learning, ICL, sometimes called few-shot learning.
Right. Here, instead of 0 examples, you provide a few, maybe 1 to 5 input-output demonstration pairs directly within the prompt itself. These examples guide the model towards the desired response style, format, or task execution.
Like giving the model a few quick examples before asking the real question.
Precisely. It helps the model understand the pattern you're looking for.
A particularly exciting area is eliciting reasoning in LLMs, making them think step by step.
Yes, using specific prompting styles to provoke logical answers, task planning, or critical thinking. These are sometimes called zero-shot reasoners, although often few-shot examples help trigger the reasoning.
Chain of thought, SHU-2 prompting is the famous one here.
Code he is key. The idea is to include step-by-step reasoning within the examples you provide in the prompt. This encourages the model to not just output the final answer, but to also generate its own intermediate reasoning steps, which often leads to much better results on complex problems like math word problems or common sense reasoning.
So showing it how to think helps it think better.
That's the intuition. FlamPolM, for instance, show that instruction tuning on Cody key formatted data significantly unlocked zero-shot reasoning capabilities.
And Cody has been improved upon.
Yes. Self-consistency builds on Cody. Instead of just generating one reasoning chain, you prompt the model to generate multiple different reasoning paths for the same problem, and then you select the final answer that appears most frequently across those diverse paths. It's like taking a majority vote over different lines of thought, making the result more robust.
More robust, less likely to make a mistake in one chain.
Exactly. And then there's tree of thought, TT, which takes it even further. It explicitly explores multiple reasoning paths in a tree structure, allowing the model to evaluate intermediate steps, look ahead, and even backtrack if a path seems unpromising. It's trying to emulate a more systematic problem-solving approach.
Building a more complex thought process, not just linear.
Right, more like how humans might explore different possibilities when tackling a hard problem,
Prompting can be simple, like single-turn instructions.
where all the relevant information is provided in one go and the LLM generates a response, as a zero-shot or few-shot. Straightforward request-response.
But for complex tasks, you need multi-turn instructions.
Yes, many complex tasks require iterative interaction. The LLM might generate a plan, take an action, like calling a tool, get feedback from the tool or the environment, and then use that feedback as input for the next turn to refine its plan or take the next step. This iterative loop is very common in designs for autonomous agents powered by LLMs.
And all of this craft around designing prompts is now called prompt engineering. It's almost a job title now.
It really is.
Yeah.
It's become an applied science or maybe an art focused on designing prompts that reliably elicit the desired behavior from LLMs, especially leveraging their zero-shot and few-shot capabilities. It's transforming how people interact with AI, even changing methodologies in fields like digital humanities, moving away from complex coding towards natural language interaction with these models. It's a testament to the power of just talking to the AI in the right way.
Okay, so we've adapted the models through tuning and prompting. Now let's pivot to efficient LLMs, reducing cost and resources. This is absolutely critical for making these powerful models practical and accessible.
Couldn't agree more. The reality is that full fine-tuning of these massive models, GPT-3 175B, Bloom's 176B, and PNLG 540B, is incredibly computationally intensive and time-consuming. It's often just not feasible for many organizations or researchers.
So we need cheaper ways to adapt them. That's where parameter-efficient fine-tuning, PEFT, comes in.
Exactly. PFT methods aim to achieve performance comparable to full fine-tuning, but by only modifying a very small fraction of the model's total parameters or by adding a small number of new parameters.
What's the trade-off? How does PFT performance compare?
Generally, PFT methods perform much better than full fine-tuning in low data scenarios. In medium resource scenarios, they're often comparable. In high resource scenarios, full fine-tuning might still have an edge, but PFT offers a massive reduction in computational cost, memory usage, and storage requirements, since you only need to store the small set of changed parameters. It's about getting the most bang for your buck.
Makes sense. What are some popular PEFT techniques?
There are several innovative approaches. Adapter tuning was one of the earlier popular methods. It involves inserting small, trainable adapter modules within each transformer block. These adapters typically consist of a layer that projects the features down to a smaller dimension, a nonlinearity, and then a layer that projects back up. Only these small adapters are trained, while the main LLM weights remain frozen.
So you inject small trainable bits into the frozen model?
Right. Variations exist, like placing them sequentially or in parallel. Atomix even uses multiple adapter modules within a single layer, learning how to combine them.
Then there's low-rank adaptation, LoRA. That one seems very popular now.
LoRA is extremely popular. The core idea is to represent the change in the weight matrices during fine-tuning, using low-rank decomposed matrices. You learn two small matrices, A and B, whose product approximates the full update matrix, delta W equally BA, while the original large weight matrix W remains frozen.
Why low rank?
Because the hypothesis is that the adaptation needed for a specific task often lies in a low-rank subspace. This drastically reduces the number of trainable parameters compared to tuning the full matrix W. A key advantage of LoRA is that during inference, you can actually fuse the learned low-rank update, BA, back into the original weights, WAUK plus BA, meaning there's no additional inference latency compared to the original model.
Ah, that's clever. No inference cost increase.
Exactly. And variations like QLoRA have even adapted LoRa to work effectively on top of 4-bit quantized LLMs, making fine-tuning extremely memory efficient.
What about tuning prompts themselves? Prompt tuning.
Right. Instead of manually engineering discrete test prompts, prompt tuning learns continuous, soft prompts. These are essentially trainable embedding vectors that are prepended to the input sequence. Only these prompt embeddings, a very small number of parameters, maybe 0.001% to 3% of the total, are tuned while the entire LLM stays frozen.
So you're learning the best instruction vector for the model.
Kind of, yes. P-tuning is a related variant. Progressive prompts build on this by adding trainable embeddings sequentially. Prefix tuning is similar, but appends trainable task-specific prefix vectors to the keys and values in the attention layers of the frozen transformer, giving more direct control over the model's internal states.
And even simpler things, like bias tuning, bitfit.
Yes, BitFit showed that surprisingly good performance could be achieved, especially on small to medium datasets, by fine-tuning only the bias terms throughout the network, freezing all the main weights. It's incredibly parameter efficient, though maybe less powerful than LoRa for larger adaptations.
Okay, besides efficient tuning, another huge area is reducing the model size and cost for inference. That brings us to quantization.
Absolutely vital for deployment. The memory and compute requirements for running inference with these giant models are a major bottleneck. You mentioned GPT-3 needing multiple high-end GPUs.
580 gigabit A100s, 350 gigabit memory in FP16, just huge.
Exactly. And larger models also present specific challenges due to the presence of very large magnitude outlier values in their activations, which can make simple quantization difficult. The goal is to significantly reduce these running costs, memory, compute energy, while preserving the model's performance as much as possible.
What are the main approaches? Post-training quantization, PTQ, sounds like the simplest.
BTQ is attractive because it requires minimal or no retraining. You take the already trained model and convert its weights and sometimes activations to lower precision formats like 8-bit integers, INT8, or even 4-bit integers.
Convert the numbers. Does that work well?
It requires clever techniques to avoid performance degradation. For instance, LLM.ant handled outliers by keeping them in full precision while quantizing the rest. SmoothQuant works by mathematically smoothing the activation distributions to make them easier to quantize accurately alongside the weights. OPTQ uses insights from optimal brain compression to quantize layer by layer, updating weights to compensate for quantization errors. OWQ gives higher precision to weights deemed more vulnerable or associated with outliers.
So it's more sophisticated than just rounding numbers.
Definitely. But sometimes PTQ isn't enough to maintain high accuracy. That's where quantization-aware training, QAT, comes in.
Training with quantization.
Yes. QAT simulates the effects of quantization during the fine-tuning process. This allows the model to adapt its weights to compensate for the precision loss, often resulting in better performance than PTQ, especially at very low bit widths like 4-bit.
What are some QAT techniques?
Alpha tuning quantizes using techniques like binary coding quantization and then fine-tunes only the scaling factors. LLM QAT generates training data from the pre-trained network and trains a quantized student model using knowledge distillation. And QLoRa, which we mentioned earlier under PAFT, is essentially a QAT method. It fine-tunes a 4-bit quantized LLM using LoRa adapters, achieving excellent results by adapting the model while it's in its quantized state using a special 4-bit normal float format for the LoRa weights during training.
Very clever combination. Beyond quantization, another way to shrink models is pruning, removing weights.
Exactly. Pruning aims to compress the model size and reduce deployment costs by removing parameters deemed unimportant.
Can this be done generally, or is it task-specific?
It can be done in a task-agnostic way, pruning the general model. However, achieving high sparsity without hurting performance is often easier when pruning for a specific task. The downside there is the high cost of potentially having to prune and deploy many different task-specific models.
What kinds of pruning are there? Unstructured pruning.
Unstructured pruning removes individual weights based on some importance criterion, like magnitude or magnitude multiplied by activation, without maintaining any specific pattern or structure in the remaining weights. Wanda, pruning by weights and activations, is a prominent example that prunes based on weight magnitude multiplied by the norm of the corresponding input activation, importantly without requiring any fine-tuning after pruning. AOL extends Wanda by allowing non-uniform pruning ratios across layers based on outlier counts.
Does unstructured pruning actually speed things up?
It reduces model size significantly, but often doesn't lead to direct inference speedups on standard hardware like GPUs because the sparse matrix operations aren't well optimized. That's where structured pruning comes in.
Removing whole groups of parameters.
Right. Structured pruning removes parameters in groups, entire rows, columns, attention heads, or even larger blocks. This maintains a more regular structure in the weight matrices, which can be effectively leveraged by hardware for faster inference. LLM Pruner, for instance, uses a 3-stage strategy. identify groups of parameters related to less important hidden states, keep the important groups, remove the less important ones, and then fine-tune briefly using LoRa to recover performance. Simple learns masks to induce sparsity in a structured way.
So structured pruning is better for speed, unstructured for maximum compression.
Generally, that's a reasonable way to think about it. There are trade-offs between compression ratio, performance impact, and potential speedup.
Okay, one final critical area of optimization. Increasing context window. Tackling long-term dependencies. This seems like a major limitation.
It is a huge challenge. Most LLMs are pre-trained with relatively limited context windows, maybe 2K or 4K tokens, mainly because the computational costs and memory requirements of the standard self-attention mechanism grow quadratically with the sequence length.
And they don't naturally handle longer sequences they haven't seen.
They often fail to generalize well to unseen lengths during inference. Positional encoding methods like ROPE, while common, don't inherently allow for zero-shot extrapolation to much longer contexts. The performance tends to degrade significantly.
But the benefits of a larger context window are massive, right?
Oh, absolutely. Better understanding of long documents, the ability to include more examples for in-context learning, executing longer and more complex reasoning processes, it unlocks many capabilities. But simply trying to expand the context length during fine-tuning is very slow, inefficient, and computationally expensive.
So what are the techniques for extrapolation or handling longer contexts?
One surprisingly effective method is position interpolation. Instead of trying to extrapolate the positional encodings beyond the trained length, studies found that simply interpolating the existing position encodings within the original pre-trained context window works remarkably well to extend the effective context.
So you sort of stretch the existing positional information?
Kind of. Techniques like YARN use NTK-aware interpolation, which scales the positional information in a theoretically grounded way for longer sequences. Often, just a very small amount of fine-tuning, maybe 1,000 steps on longer sequences using interpolated positions, can achieve good results on much larger context windows. Many recent models claiming long context capabilities use variations of this.
What about changing the attention mechanism itself? Efficient attention mechanism.
Yes, that's another major approach.
Yes.
Since dense global attention is the bottleneck, researchers have developed variants like local attention, only attending to nearby tokens, sparse attention, attending to predefined patterns, and dilated attention.
Dilated attention, like in convolutional networks.
Similar idea, yeah. LongNet replaces standard attention with dilated attention, where attention patterns have increasing gaps or dilation factors at different layers, allowing it to scale theoretically to sequences of up to 1 billion tokens while maintaining reasonable computational cost. LongT5 proposed transient global attention, T-global, combining local attention with attention to a few selected global tokens, improving task performance on longer inputs with fine-tuning. ColdT5 uses 2 branches, a lightweight one for all tokens and a heavyweight one for important ones. Long LoRa uses a shift short attention during fine-tuning, but removes to dense attention during inference, cleverly achieving long context adaptation efficiently.
Can you have longer context extrapolation without training at all?
There are some attempts. LM Infinite uses a clever shaped attention mask and distance limiting within the original context window size to process longer sequences without fine-tuning. Parallel context windows, PCW, is another interesting idea. It chunks the long input into segments that fit the pre-trained context length and processes them, applying the same positional encodings to each chunk, essentially trying to stitch context together without retraining. These are often less robust than fine-tuning methods, but offer potential for using existing models on longer inputs.
Okay, this is fascinating. Now let's explore how LLMs are being extended beyond just processing the text you feed them. This is where they start interacting with the outside world, using external knowledge, planning actions, really pushing the boundaries.
Absolutely. This section highlights the evolution of LLMs from being essentially sophisticated text processors to becoming more dynamic, interactive systems. Augmented LLMs tackle issues like factual consistency and knowledge cutoffs, while LLM-powered agents and multimodal models represent significant strides towards more holistic, capable AI.
So first up is augmented LLMs, beyond internal knowledge. A key concept you mentioned is grounding. What does that mean here?
Grounding in this context refers to the process of providing LLMs with relevant, use case-specific information alongside the user's prompt. This external information helps to improve the accuracy, relevance, and overall quality of the generated response.
Why is that necessary? Don't they learn facts during pre-training?
They do learn a lot of factual information, but it's static frozen at the time of training and often implicit. LLMs fundamentally act more like engines, for generating probable text sequences rather than reliable knowledge stores. They lack an inherent awareness of factuality or whether their internal knowledge is up to date. Grounding provides that external check.
That makes sense. And this limitation directly leads to the need for retrieval-augmented LLMs.
ROM. Precisely. The core problem ROM addresses is that LLMs have this limited, often outdated internal memory, which frequently leads to inaccurate responses or hallucinations, confidently stating things that are incorrect.
So ROM fixes this by fetching information.
Exactly. The solution is to retrieve relevant, potentially up-to-date information from an external knowledge source like a database, a document collection, or even the live web, and provide that information to the LLM as part of its context when generating the response.
And the benefits are clear. More accurate answers, potentially with references.
Right. It enables accurate answers grounded in verifiable sources. What's really impressive, as we touched on, is that smaller models, when augmented with retrieval, can often perform comparably to much larger non-augmented models. For instance, an 11B parameter retrieval augmented model was shown to be competitive with the massive 540B PaLM and a 7.5B model with the 280B Gopher. It's a very efficient way to enhance capability.
What are the main components of a ROM system?
Generally, there are two major components. First, a retriever, which takes the user query and finds relevant documents or passages from the external knowledge source. This could use traditional methods like BM25 or dense vector similarity search. Second, the language model itself, which takes the original query plus the retrieved context and generates the final response. It's like giving the LLM access to a real-time, searchable library for every query.
How is this retrieval augmentation actually implemented? Are there different strategies?
Yes, several strategies exist. The simplest is zero-shot retrieval augmentation. Here, you keep the LLM's architecture and weights completely unchanged. You just use an off-the-shelf retriever, like BM25 or maybe embeddings from a frozen BERT model, to find relevant context, and then you simply prepend that context to the user's query before feeding it to the LLM.
Just stuff the retrieved text into the prompt.
Basically, yes. This can even involve multiple retrieval iterations, where the LLM's initial output helps refine the query for a subsequent retrieval step, as seen in systems like Flare or RepoCoder.
But sometimes you need to train the components together, training with retrieval augmentation.
Right. To potentially get better performance or tighter integration, you can train or fine-tune either the retriever, the LLM, or both within a retrieval augmented generation RAG pipeline.
How would you train the LLM with RG?
You could pre-train smaller LLMs with the retrieval mechanism built in from the start, as Retro demonstrated. They showed this could allow smaller models to outperform much larger non-RAG models. Alternatively, you might focus on training the retriever itself, teaching it to fetch better, more relevant documents or passages specifically for the downstream LLM, maybe using contrastive learning while keeping the main LLM frozen.
Or train both together.
Yes. You can train the retriever and LLM jointly, allowing error signals to propagate back from the LLM's generation task to update both the retriever and the generator. This might use objectives like masked language modeling on the combined input or predicting which document chunk a sentence came from.
What about more sophisticated ways to combine the retrieved info than just prepending?
Good point. Encoded context augmentation, exemplified by the Fusion Decoder FAD architecture, is a popular approach. Instead of just concatenating text, FAD independently encodes each retrieved document chunk and then fuses these representations directly into the LLM's decoder layers using cross-attention. This allows the model to attend to information from many documents simultaneously without making the input sequence excessively long.
And increasingly, retrieval isn't just from local databases, but the web-augmented LLMs.
Exactly. To address the limitations of static or outdated local knowledge stores, many systems now retrieve query-related context directly via live web searches using APIs like Bing or Google Search. This ensures the LLM has access to the most current information when generating its response. Tools like WebGPT explored this early on.
Okay, so retrieval gives LLMs better knowledge. What about giving them the ability to act? That's tool-augmented LLMs.
Right. While retrieval augmentation primarily provides passive information, tool augmentation is about enabling LLMs to interact with external tools or APIs to actively accomplish tasks they couldn't do on their own, like performing calculations, searching databases, booking flights, or even controlling software.
How does that work? What's the concept?
The core concept is that the LLM leverages its powerful reasoning and planning abilities to break down a complex user request into a sequence of steps. For each step, it might decide it needs to use a specific tool, generate the correct input for that tool, like an API call, execute the tool, and then parse the tool's output to inform the next step or generate the final response.
So the LLM becomes a sort of orchestrator of tools.
Exactly. The generic pipeline often looks something like this. Plan the task. Select the appropriate tool. Execute the tool with the right arguments. Inspect the tool's output. Generate the next step or final answer. This loop might involve modules like a retriever to find the right tool or documentation, a tool execution environment, memory to store intermediate results, and feedback mechanisms.
And again, are there different strategies here? Can they use tools without specific training?
Yes, remarkably often. With zero-shot tool augmentation, LLMs can interact with tools they haven't been explicitly trained on, relying purely on their in-context learning and reasoning abilities, often guided by descriptions of the tools provided in the prompt.
Just tell the LLM what the tool does and it figures it out.
Sometimes, yes. Systems like ART, automatic reasoning, and tool use build libraries of task examples showing reasoning steps and tool calls, then retrieve similar examples at runtime to help the LLM generate a plan for a new task. Other work has shown that providing detailed tool documentation, like API specs, directly in the prompt can be enough for models like REST-GPT to interact with the RESTful APIs, or for Toolkin-GPT, which cleverly represents tools as special toolkins the LLM can generate.
But for more robust or complex tool use, you probably need training with tool augmentation.
Generally, yes. Fine-tuning the LLM specifically on datasets demonstrating tool interaction can significantly enhance its planning abilities and reliability beyond zero-shot limitations. Gorilla, for instance, instruction tunes Llama using a large dataset of API calls retrieved from documentation, similar to how self-instruct data is generated. Tall uses self-play between the LLM and tools to generate learning signals. ToolLM collected a massive dataset of 16,000 real-world APIs and automatically generated high-quality instruction tuning data showing how to plan and execute API calls to fulfill user instructions using a sophisticated decision tree search to ensure diversity and correctness.
And this is expanding into multiple modalities too, multimodal tool augmentation.
Yes, the frontier is moving towards allowing the compositional reasoning of LLMs to manipulate tools that operate in multimodal settings, involving both text and images, for example. The LLM might outline a plan execute, inspect, generate, that involves using visual tools like image editors or object detectors alongside text-based ones, either using a powerful multimodal LLM directly or having a standard LLM plan the sequence of multimodal tool usage.
This seems to naturally lead us into LLM-powered agents, the brains of autonomous systems. This is where LLMs go beyond just responding to requests and start acting more like cognitive controllers.
Exactly. This is where the LLM isn't just a component being augmented, it's the central cognitive controller or brain of an autonomous system. It's responsible for planning complex tasks, reasoning about the world, incorporating memory of past interactions, and adapting its behavior based on feedback from the environment or tools.
What are the key modules and strategies that enable this? Planning and reasoning seem central.
Absolutely crucial. The planning and reasoning capabilities of LLMs are fundamental here. Prompting methods we discussed earlier, like chain of thought, state order, tree of thought, Tourdier, and self-consistency, are often used to elicit the LLM's reasoning and guide its selection of actions or plans. LLMs have shown they can generate surprisingly effective action plans directly from high-level task descriptions, even without specific fine-tuning for planning. More advanced methods like reasoning via planning, RAP, explicitly use the LLM as a world model to simulate future outcomes of potential actions, while Retroformer uses a retrospective LLM to provide helpful context from past attempts to improve current planning.
And for a system to be truly autonomous, it needs feedback, right, to learn from its actions.
It's essential. This creates closed-loop systems. The response or outcome from an action taken by the agent is fed back to the LLM. The LLM can then use this feedback to reassess the situation, update its understanding or plan, and decide on the next action. The reflection framework is a great example of this, using feedback to iteratively refine plans. Interestingly, LLMs themselves can also be trained or prompted to act as reward functions, evaluating the success of actions taken by other policies, which is a fascinating shift from relying solely on human-defined rewards in RL.
How do these agents handle memory over longer interactions?
That's another key component. Since LLMs have limited context windows, agents typically rely on external memory modules to store interaction history, observations, or learned knowledge. Reflection uses a form of episodic memory to store past trajectories, sequences of states, actions, rewards, which can be retrieved to inform future decision-making. Retroformer employed both short-term memory for recent interactions and long-term memory, which summarized past failed attempts used for reflection and prompts. Effectively managing and retrieving from memory is critical for long-horizon tasks.
We're even seeing multi-agent systems powered by LLMs.
Yes, that's a rapidly growing area. You can assign different LLMs specific user-defined roles or personas, e.g. software engineer, project manager, code tester. These LLM agents can then collaborate, communicate, and interact within a simulated environment to complete complex tasks that might be difficult for a single agent. It's like creating a virtual team. Coding is a popular application area for this.
What about interacting with the real world? LLMs in physical environment. That seems like a huge leap.
It is a huge leap and a major challenge because LLMs inherently lack grounded, real-world experience. But researchers are finding clever ways to adapt them. The SACAN system, for example, bridged this gap by making the LLM aware of the robot's low-level capabilities or affordances. The LLM would propose a high-level plan, say, and then a separate affordance function would determine which of those steps were actually possible for the robot to execute, in the current physical state.
So the LLM plans, but something else checks feasibility.
Exactly. More integrated approaches like PaulM involve training large multimodal LLMs directly with sensor inputs,
Right.
like images, proprioception, alongside language, allowing them to solve physically grounded tasks end-to-end.
This integration extends to manipulation and navigation too.
Yes. In manipulation, LLMs are being used to enhance robot dexterity and adaptability. They can analyze visual and spatial information to help with tasks like object recognition, determining grasp points, or facilitating human-robot collaboration. In navigation, LLMs can improve how robots navigate complex environments by generating feasible paths and trajectories, taking into account intricate details described in natural language or observed through sensors. This is invaluable in dynamic settings like warehouses or autonomous driving.
Okay, the final expansion, multimodal LLMs, MLMs. Perceiving beyond text, this is about giving LLMs eyes and ears, essentially.
Pretty much. It's about enabling LLMs to process and understand information from different modalities beyond just text, primarily images, but also video and audio. It's truly bringing AI closer to the richness of human perception.
What are the main benefits of making LLMs multimodal?
The benefits are profound. By incorporating information from various senses, MLMs can achieve a much deeper understanding of context. This leads to more intelligent, grounded, and expressive responses. It allows for closer alignment with how humans perceive and interact with the world, which relies on multiple senses. And it enables more intuitive and flexible user interfaces. Imagine just showing an LLM a picture and asking questions about it.
How are these MLMs actually built? Are there different approaches?
Yes, researchers are exploring three main construction streams. The first is pre-training unified end-to-end models from scratch or near scratch. Flamingo from DeepMind was an early example using gated cross-attention layers to fuse information from pre-trained and frozen vision and language encoders. BLAP2 proposed a more efficient two-stage strategy using a querying transformer, QFormer, to bridge the gap between frozen image encoders and frozen LLMs. Mini-GPT-4 took this further, achieving impressive results by training only a single linear projection layer to align features from a frozen vision transformer, VIT, and QFormer with a frozen vicuna LLM.
So leveraging existing powerful models seems key. What's the second stream?
The second stream is fine-tuning. This takes an existing powerful pre-trained text-only LLM and extends it with multimodal capabilities, usually through instruction tuning on multimodal data. The key challenge here is collecting enough high-quality multimodal instruction-following data, pairs of image-text input and text output.
How do they get that data?
Various methods are used. Adapting existing vision language benchmark datasets, using self-instruction techniques, prompting multimodal models to generate data, or creating hybrid compositions. Another approach within fine-tuning uses lightweight, learnable interfaces or adapters, like Llama Adapter or Lavin, which efficiently connect frozen pre-trained vision models to frozen LLMs with minimal trainable parameters. Alternatively, some systems use expert models, for example. Video chat text uses Whisper for speech recognition to directly convert other modalities into text that the LLM can then process.
And the third stream is prompting, using prompts for multimodality.
Yes. Similar to text-only prompting, this aims to guide MLLMs using context, examples, or instructions provided in the prompt without changing the model's parameters. This is particularly useful as it reduces the need for massive multimodal training datasets. It's being used effectively for multimodal chain-of-thought SQL problems.
Multimodal SOT, like reasoning about images step by step.
Exactly. Systems like multimodal code use a two-stage approach, where the MLLM first generates a textual rationale based on the image and text input, and then uses that rationale to infer the final answer. CoTP key tries to implicitly generate the reasoning within the final output. LLMs can also be prompted with multimodal descriptions and available tools to effectively divide complex multimodal tasks.
And a big application area here is visual reasoning.
Definitely. LLMs are significantly advancing visual information analysis and visual language integration. Compared to older, more specialized visual question answering (VQA) systems, LLM-aided methods offer stronger generalization across tasks, emergent abilities like OCR or detailed description learned implicitly, and much richer interactivity. Techniques like PointClip v2 leverage LLMs to generate 3D-specific prompts for better point cloud understanding, while GPT-4 tools uses LoRa fine-tuning to teach LLMs how to use external visual tools based on instructions. In many complex visual reasoning tasks, the LLM effectively serves as the central controller, decision maker, or semantics refiner, orchestrating other vision-specific modules or interpreting their outputs.
Okay, wow. It's undeniably clear that LLMs are transforming, well, nearly every field imaginable. Medicine, robotics, science, finance. Their generalizability is truly impressive.
It really is remarkable how broadly applicable these models are proving to be.
But as the saying goes, with great power comes. Well, you know the rest. We absolutely need to talk about the significant challenges that still need to be addressed. There are quite a few.
Indeed. While the opportunities are enormous, it's crucial to acknowledge the intrinsic technical challenges, things like computational cost, reliability, interpretability, and also the emerging societal issues around privacy, bias, and control. For the research community, these challenges really define the frontier of innovation and highlight where the next breakthroughs are urgently needed.
So let's start by quickly recapping the broad applications of LLMs, just to set the stage for the challenges. We see them as general-purpose tools now, right? Personal assistants, helping draft emails, generating creative content, powering customer service chatbots, even assisting with data analysis, filtering, summarizing, finding patterns.
Absolutely. And in specialized fields like medicine, they're aiding clinical decision support, improving patient interaction via chatbots, accelerating medical research by processing vast literature, supporting medical education, and even assisting in public health surveillance.
In education, we see personalized learning paths, support for teachers with planning and grading, tools for language learning, and significant improvements in accessibility through transcription and text simplification.
In science, they're helping researchers analyze and summarize literature, stay updated, formulate hypotheses, and improve scientific writing. In mathematics, they can explain problems step by step, guide proofs, and translate complex concepts.
For law, they assist with analyzing legal documents, explaining terms grounded in case law, and potentially aiding legal reasoning. In finance, specialized models like Bloomberg GPT show superior performance, while open-source models like FinGPT enable applications in robo-advising and trading, often by breaking down complex tasks into actionable steps.
And finally, in robotics, as we discussed, they're enhancing human-robot interaction, task planning, navigation, manipulation, and enabling robots to learn continuously and adapt more effectively.
Okay, so the potential is vast. But now, the critical challenges and future directions. The first, and maybe the most fundamental, is simply the computational cost.
It's immense. Training these state-of-the-art models requires extensive computational resources, thousands of high-end GPUs running for weeks or months. This translates to extremely high development and production costs, significant energy consumption, and growing environmental concerns.
And we're hitting diminishing returns.
It seems so. While performance generally improves with more compute, the gains often follow a power law, meaning you need exponentially more compute for linearly smaller improvements in performance, especially once model and dataset sizes are very large. Making them bigger and bigger isn't sustainable indefinitely.
A pervasive and widely discussed issue is hallucinations, models making stuff up.
Right. Generating plausible-sounding but factually incorrect or nonsensical statements. These can be categorized based on what they contradict, the input prompt, input conflicting, the preceding generated context conflicting, or known world facts, fact conflicting.
What causes them?
It's complex. Contributing factors include a lack of grounding in real-time knowledge, overfitting to patterns in noisy training data, underfitting leading to overly generic statements, or divergence between the training data sources and reliable references. Fundamentally, we have to remember LLMs are primarily language models, optimized to predict probable sequences, not knowledge models guaranteed to be factual. They generate based on statistical likelihood, not truthfulness.
How can we mitigate this? Retrieval augmentation helps.
Retrieval helps provide grounding. Validating responses against external knowledge graphs or databases is another important mitigation strategy, but it remains a major open challenge.
Then there are the significant ethical concerns around biases and fairness.
Yes. LLMs inevitably learn and can even amplify the societal biases present in their vast training data, which reflects historical and societal inequalities. This can lead to unfair, discriminatory, or stereotypical outputs, posing serious ethical risks. Debiasing these models effectively, without harming their capabilities, is an incredibly important but still largely unresolved task.
Closely related is the tricky balance between overfitting memorization versus generalization.
Right. LLMs can be susceptible to overfitting noisy or spurious patterns in the training data, which can lead to illogical or nonsensical responses. On the other hand, they need to memorize some information to answer factual questions accurately. The challenge is striking the right balance. Enough memorization for knowledge recall, but enough generalization to handle novel inputs and avoid simply regurgitating training examples inappropriately. Too much memorization hinders flexibility and increases privacy risks.
The sheer complexity of these models also leads to issues of stability and opacity.
Definitely. Stability refers to the phenomenon where very small, often semantically meaningless, perturbations to the input can drastically change the model's output. This makes them unpredictable. Opacity, or the black box nature, stems from their immense size and complexity, making it incredibly difficult to understand why they make specific decisions or generate certain outputs.
Which impacts trust and debugging.
Exactly. It limits trust and makes it hard to debug failures, especially in sensitive applications like medicine or finance. Probing techniques try to indirectly analyze the model's internal representations to get some insight into what they've learned about language or the world, or to detect biases, but they don't provide full transparency.
And this concentration of complexity and cost leads to economic and research inequality.
Yes, unfortunately. The extremely high costs associated with training and deploying state-of-the-art LLMs mean that their development is largely concentrated within a few very well-funded tech companies and research labs. This risks creating a significant divide and worsening inequalities in AI research capabilities and access to powerful AI tools.
Despite their impressive language skills, they still have reasoning and planning limitations, don't they?
They do. While they can generate text that looks like reasoning, especially with techniques like chain of thought, they often struggle with tasks requiring robust, common-sense planning, complex multi-step logical deduction, or rigorous mathematical reasoning. Tasks that humans find relatively easy can still stump them. This goes back to them primarily generating likely text completions rather than executing guaranteed logical operations.
Another practical challenge is their limited knowledge. It's static, right?
Yes. The knowledge implicitly stored in an LLM's parameters is essentially frozen at the end of its pre-training phase. It can quickly become outdated, especially in rapidly evolving domains. Retraining these massive models frequently is prohibitively expensive. Retrieval augmentation is a key strategy to inject up-to-date information, but efficiently adapting the entire training and deployment pipeline to work seamlessly with Array is still an ongoing area of research.
And of course, there are major concerns around safety and controllability.
Huge concerns. There's a significant risk of LLMs generating harmful, toxic, biased, misleading, or otherwise inappropriate content, either accidentally or when prompted maliciously. Ensuring their safe utilization and preventing misuse is a critical challenge. Models remain susceptible to jailbreaking prompts designed to bypass safety filters and adversarial probing. Red teaming helps identify vulnerabilities and collect data for safety fine-tuning, but it's an ongoing battle.
This ties into security and privacy as well.
Absolutely. LLMs can inadvertently leak sensitive personal information present in their training data. They can generate false or unethical responses. And they are vulnerable to various security attacks, backdoor attacks inserted during training, jailbreaking and prompt injection attacks at inference time, or even data poisoning attacks targeting the training data itself. Developing robust defense mechanisms against these threats is essential. The memorization issue also poses a privacy risk, as specific training phrases can sometimes be extracted through carefully crafted prompts.
As we move into more advanced capabilities, multimodality presents its own set of unique challenges.
Yes. Integrating information from diverse modalities like text, images, audio, and video is complex. Key challenges include effectively aligning representations across different modalities, developing optimal fusion strategies to combine multimodal information, and managing the significantly higher computational demands associated with training on and processing diverse, often much larger, multimodal data sets.
We also mentioned catastrophic forgetting earlier. models losing old knowledge when fine-tuned.
Right. When you fine-tune an LLM on a specific domain or task, it can sometimes forget the general knowledge or capabilities it learned during pre-training. This is particularly problematic if you want the model to be both specialized and generally competent. Techniques like replaying some pre-training data during fine-tuning or using PFT methods that minimize changes to original weights can help mitigate this, but it remains a challenge for continual learning.
And adversarial robustness is still a major hurdle.
Definitely. LLMs remain highly vulnerable to adversarial examples, subtle, often human, imperceptible changes to the input that are deliberately crafted to mislead the model and cause it to make incorrect predictions or generate undesirable output. Enhancing robustness against such attacks, often through adversarial training, can sometimes come at the cost of reducing the model's generalization performance on clean data. Finding the right trade-off is crucial, especially for safety-critical applications.
The black box nature leads back to interpretability and explainability challenges.
Exactly. The lack of transparency into how LLMs arrive at their decisions hinders trust, accountability, and our ability to fully understand their failure modes. This is a major barrier to adoption in high-stakes domains like healthcare or legal reasoning. Significant research efforts are focused on developing techniques to make LLM behavior more interpretable and explainable, fostering user trust and enabling more responsible AI development.
For widespread deployment, especially on smaller devices, real-time processing is still tough.
Very tough. The high computational demands for inference, combined with the large memory footprint for storing weights, impede real-time performance, particularly on edge devices or mobile phones. The sheer number of layers and parameters in large models leads to significant inference latency.
And even with longer context windows, long-term dependencies remain a challenge.
Yes, while progress has been made, truly handling very long-term dependencies, maintaining coherence, remembering details from much earlier in a long conversation or document remains difficult for current architectures. This can lead to inconsistencies or forgetting key context over extended interactions.
This all seems to loop back, in part, to hardware acceleration. We need better hardware.
The rapid growth in LLM size and complexity continues to outpace hardware progress, to some extent. GPUs are crucial enablers, but inference in particular remains costly and energy-intensive. Techniques like model quantization and pruning help bridge the gap by making models runnable on existing hardware. Specialized hardware accelerators, like TPUs or custom AI chips, can further reduce cost and latency, but they don't fully resolve the fundamental limitations and often require specialized software optimization. Continuous innovation in hardware is essential.
Finally, overarching all of this is the need for regulatory and ethical frameworks.
Absolutely critical. The pace of LLM advancement is incredibly fast, necessitating careful societal consideration and oversight to manage the associated ethical and social challenges, issues like misinformation generation, job displacement, accountability, bias amplification, and potential misuse. Developing proactive, adaptive ethical guidelines, policy measures, and robust auditing mechanisms is essential to ensure these powerful technologies are developed and deployed responsibly and beneficially. Governance is lagging behind capability right now. What's really fascinating here, I think, is that despite the immense progress we've seen, the field is still grappling with really foundational questions. It's not just about how do we build bigger models anymore. It's increasingly about how do we build better, more reliable, more understandable, and more aligned models. Models that can truly understand and interact safely and beneficially with our complex world.
Yeah, that's a great summary. So, what does this all mean for you, the expert listener looking ahead? We've seen the breakthroughs are happening at just an incredible pace, from architectural innovations like Mixture of Experts to the really nuanced art and science of prompt engineering and this critical ongoing need for alignment. But the challenges, hallucinations, bias, the sheer cost and carbon footprint, these aren't just technical hurdles, are they? They're deeply intertwined ethical and societal considerations that demand our collective attention and effort. The ultimate goal, it seems, remains AI that's not only incredibly intelligent, but also genuinely trustworthy and beneficial for humanity.
Well said. That's the hope and the challenge.
So as we wrap up this deep dive, maybe here's a provocative thought to leave you with. If LLMs are rapidly mastering the art of language, and language is arguably our primary tool for shaping thought, culture, and reality, what new realities will these models enable us, or perhaps compel us to construct? And crucially, what responsibilities come with that newfound capability to shape reality through language at unprecedented scale?
That's a deep one.
Yeah.
Something to definitely ponder.
Indeed. Well, thank you so much for joining us on this very in-depth exploration. We really hope this deep dive has provided you with a clearer, more structured picture of the current landscape and the future directions of large language models.
Hope it was useful.
Until next time, keep exploring, keep questioning, and keep pushing the boundaries of AI.